So do you remember how to find the local max and minimums and minimums back in Calc 1? We found the critical points. We did the first derivative test. Have you guys heard of the second derivative test? There's first derivative test and second derivative test. And then if we want to go farther, there's this idea of finding inflection points and things like that. In Calc 3, it's a little bit different because our most effective test back in Calc 1 was the first derivative test. And the first derivative test basically took a critical point and went from the left to the right to see if it went up and down or down and up or up and up or down and down, and figured out whether it's max or min. So unfortunately, for these functions, there's not just one direction we're looking at. We're not just going from left to right. If you remember, we're going in all kinds of different places. So if we have a critical point somewhere up on top, you can't just pick a particular random direction to figure out whether it's a maximum or a minimum. This could be a maximum, minimum in many different ways. So we have to rely on what's called the second derivative test, which is an extension of the second derivative test back in Calc 1, and rely on the second derivative. Second derivative, if your function takes a two-dimensional input and outputs a scalar, this is a function, multivariable function, our second derivative is a little tricky, right? How many second derivatives are we going to have? 3? 4? Technically we have 4, but 2 of them are probably going to be equal to each other. So it's those mixed partial derivatives that we'll run into. We'll get to that point later on. But for now, let's first define a critical point. And a critical point is basically when your first order partial derivatives are equal to 0. And they have to be equal to 0 at the same time. So that's a little tricky because one of them might be equal to 0, and then the other one might not be equal to 0 at that particular point. So we have to make sure that they're equal to 0 at the same time. And that's one of the bigger problems that we're going to run into in terms of the calculations. The theory, I think it's simple enough to understand. If you have a slope 0 in the x and a slope 0 in the y, then that's a pretty good candidate to have a flat horizontal tangent plane at that point. That makes sense. If going along the x you're flat, but going along the y you're not flat, then that's probably not a good critical point to look at. So that's why they both have to be 0 at the same time. And for this, I just want to see if I can find some examples. I didn't look earlier, but let's see if I can look now. Find some examples where we're actually trying to compute or find the critical points. So let's just say we're just looking for critical points at this point. That's my, I suppose I should say CP for critical points. It's better than crits. But CP, when I was growing up, was a gang in our neighborhood. I don't usually use CP. Crocker Park. So critical points, let's say for number 5, if we're looking for critical points, let's practice finding critical points. Number 5 has, I need to find the fx derivative with respect to x. Looks like a 2x plus y. and then everything else is 0. And then fy is going to be x plus 2y plus 1. And I want to set that equal to 0. So the thing is, I want to set both of these equal to 0 at the same time. And the tricky part about this is that there is not one single way to do this, and it could be different every time. There might be some methods that could be the same for a couple of problems, but when you look at enough of these problems, you'll see that there's a lot of different ways to do this. So I'm going to start with 2x plus y equal to 0. I'll set that equal to 0. And maybe just solve for one of the variables, y is equal to negative 2x. I don't know if that's helpful. But at this point now, I can set the second one equal to 0, x plus 2y plus 1 equal to 0. And now I can combine them since my y is equal to negative 2x. Maybe if I put negative 2x there in for y, I can possibly get a value here. So let's see how that happens. I get x minus 4. Oops. This should be an x, yeah? So x minus 4x plus 1 equals 0. Negative 3x plus 1 equals 0. So x is equal to negative 1 divided by negative 3. X equals 1/3. And remember, the domain here, the points that we're looking for are ordered pairs. We need an x and a y, so just plug that in for x to get the y. Y is equal to negative 2 times 1/3. That's negative 2/3. So for this particular problem, it looks like I have one critical point, and then that's all I get. Yeah?
I don't understand how this can get more complicated when you have two equations and two unknowns. Like, you're always going to have two equations and two unknowns, right? It's just how you solve it's going to be different. I mean, like, if you have a quadratic where you have a whatever. Okay, so that's the difference. It's not like just going to be the types of equations that we're plugging stuff into, but it's still going to be two equations, two unknowns.
Yeah, it's still two equations and two unknowns.
Okay. It's not more complicated.
Maybe I was just trying to scare you. I don't know. What? Like f of x, y, z? Yeah, yeah. You can go. We'll see if there's an example like that. I wasn't planning to go over anything like that, but if there is an example, we'll do it. Let's try another one. Let's take one that's to the third power and see how, I don't know if this is going to be much more difficult than the one we just did. So let's compute fx and fy again. So fx looks like it's going to be 6xy minus 12x, and everything else is 0. With respect to y, this is 3y squared plus 3x squared, 0 minus 12y, and then 0. Did I do that correctly? So I'll set each of them equal to 0 and see what happens. We get 6xy minus 12x equal to 0. And in this particular case, I can factor out a 6 and an x. That'll leave me a y minus 2 equal to 0. So x is equal to 0 and y is equal to 2. So these are the possible zeros for the fx, and I need to match this up with possible zeros for the fy. And so it'll be a different colored pen here. So what I could do is, at this point, I can put 0 in for x and then try to figure out what y is equal to. So I need my fy to equal to 0. I got 3y squared plus 3x squared minus 12y is equal to 0. And maybe in place of x, I'll put 0 in and see if I can solve for y. Right? So I have this term, middle term going away. I have a 3y that I can take out. I have a y minus 4 equals 0. So I have y is equal to 0 and y is equal to 4. So with x is equal to 0, I have these two other points to match it up with. So far, we have 0, 0, and 0, 4 for critical points. Now I need to take the 2, put that into the equation, and then set that equal to 0. So this is 3y squared plus 3x squared minus 12y is equal to 0. And then for y, I'll put 2. So we got 12 minus 24 is equal to 3x squared. Oops, let's say plus 3x squared right now. So we'll bring the 12 over to the other side, divide by 3, and take the square root. X is equal to plus and minus 2. Whoa, did I do that right? I kind of went quickly. So this is what I noticed when I was doing that presentation, wasting my time, is that I had to actually check my answer. When I'm lecturing, I just stop and say, is that right? And you guys just tell me yes or no. Over there, I don't have anybody to ask, is it right? So I have to actually check it. So I got a couple more. 2, 2, negative 2, 2. So remember, the x is positive and negative 2, and the y is 2. So here are my complete list of critical points. I have 4 critical points for this problem. So you see how it kind of gets tricky, and you just have to be careful about using your the bottom line is 2 equations and 2 unknowns. And then however you can solve that. If it's linear, then it's a piece of cake. If it's not linear, then you got to do some sort of weird substituting. And keeping a track of, how we have 2, and then for each of these 2 possibilities, we came out with 2 more, so that becomes 4. So it gets a little tricky when you start messing around with stuff like that. Like something like number 8, you got exponential functions to work with also. Okay. All right. So that's the story. The critical point, usually in Calc 1, when we say critical point, you just say x is equal to 5, and then that's your critical point. But yes, you can most definitely make the z value involved here. Yeah, you just need to plug it in. So yeah, for this first example that we had, for this first function, x is equal to 1/3, y is equal to negative 2/3. And so z is whatever you get when you put 1/3 in for x and negative 2/3 in for y. Yeah? Not necessarily, because it could be inflection. Pardon me? Oh, saddle, yeah. Could be a saddle point. So this is where I'd say you guys can find out what this is, right? Versus in the video where I had to actually find it myself. But I used Mathematica, so it should all be correct. And yes, you can find the z components for these things. 0, 0. I'll do this one. If I put 0 in for x and y, I get 2 for z. And then you guys can do the rest. So it depends on what they're asking for. If they're asking for the critical points, it's just the input values, then the x and y would be fine. If they're looking for the critical points as the x, y, z values, then you would put all three of them. Sometimes they might just look for the maximum value, the minimum value, in which case you just put the z value. That's the output value. So it depends on what they're asking for, how they're asking for it. And especially if it turns out to be one of those word problems where they're not necessarily asking for the xy point, they're not necessarily just asking for the z value, they're asking for a combination or something else, then you just have to answer the question that they have. All right? So that's finding critical points. Now, after finding critical points, we want to know if we have a maximum or a minimum. And the first approach is to take a look at whether something is a local max or a local min, or if it's not a local max or a local min, maybe it's something else. And for that, I said that the first derivative test isn't going to work out for us because we have to go in infinitely many directions. The first derivative test in Calc 1 just tells you to check to the left and check to the right and figure it out from there. So we have to rely on the second derivative test. And the second derivative for functions of one variable in Calculus 1 was just easy. Just take the derivative again, take the derivative twice, and then you get the derivative function. But if it's a multivariable function, the derivative is a lot more strange looking. And so what they have here in our second derivative test for multivariable functions, or functions of two variables, is that the d is, I want to call it the discriminant. They don't make note of why it's called d, but d is called the discriminant of some sort. And it actually is relying on a bunch of second derivative, combination of second derivative functions, second order partials. So if you see here, we got fxx and fyy, and then fxy squared. And so they make a note that if that's too hard to remember, write it down. If that's too hard to remember, you can try to think about the discriminant as a determinant of a matrix. And the matrix is a matrix of second order partial derivatives. And so if you want to try to remember this, you can think about this as a matrix of mixed order partial derivatives, second order partial derivatives. We got fxx and fyy in the corners, and then fxy and fyx in the, I guess these are the diagonals, and fxy and fyx are in the wings. So that the determinant of that is fxx, fyy minus fxy and fyx, which for most of these nice functions are equal, so they just have that fxy squared. So in Calc 1, we looked at the second derivative, the sign of the second derivative, whether it's positive or negative, after you put the critical point in there. And the critical point here is AB. So in matrix theory, it turns out that matrices have signs, and I'll say signs in quotes, whether they're positive or negative. Now, a matrix is a collection of numbers, right? So it's hard to think about this as just one sign. But it turns out that if we take a look at the whole determinant, and the whole determinant being positive, and then a subdeterminant of a submatrix that's going in this diagonal way, whether this is positive or negative, that kind of tells a sign of the matrix. So when you have a positive determinant total and then the sign stays positive, it's like having a positive second derivative. And you remember the positive second derivative is concave up. You can think about this as like a special derivative too for multivariable functions. If you think of something being concave up, think of a paraboloid that's concave up, that's holding water. And the critical point is down here, so it's a minimum. So when the determinant and the corner functions are both positive, then the whole thing is positive. We have a concave up situation. If it changes sign from positive to negative, then that's when you have a concave down situation. And the concave down situation will give you a local maximum. Now, if your determinant is negative, that's a totally different story. And it turns out that if your determinant is in fact negative, then you have something that's neither a max or a min. And I don't know why they bothered saying not a local max or a min. You actually get something more definite here. It's a saddle point.
Could it also like not actually exist? Well, it could exist, but like like a cutoff point, or
Yeah, some of those like cutoffs or corners or something like that. Then then the critical point won't be a critical point, or it would be a critical point where it's undefined. In which case, that's something more complicated to deal with. So for our purposes, we're just going to be dealing with nice functions. And another thing that they missed out here, which is another thing that they missed out, they always don't say it, but they talk about it, but I think it's worth saying. And that is, we got D being bigger than 0, or this looks like a bigger than or equal to. I better erase that. They talked about D being positive or D being negative, but what if it's equal to 0? If D is equal to 0, then we're kind of out of luck, just like the second derivative test. We have no conclusions. It could be a maximum, it could be a minimum, it could be a saddle, or it could be just nothing. Maybe line or a plane, but then they probably wouldn't be critical points. So I can't think of one. Yeah, maybe I'll think about it. Maybe I won't. Thanks. All right, there's just all it is no conclusion, so we just have to accept it. Yeah, because these are nice functions, we can assume that they're going to be equal to each other. So the strange functions would be some functions that are not continuous, or some weird functions that are continuous but the first derivative doesn't exist, or some weird thing like that. That only happens in weird situations. All right. So let's take a look at our example from here, number 5. We found critical points already. So let's just take that as our example. Just going to quick copy this, and then quick copy the critical point. So as our first example, let's say we're looking at this function and we have this critical point. Now we need our derivatives too. Let's just redo our derivatives. So we'll do our fx. This is 2x plus y. Our fy is x plus 2y plus 1. And then from here we need our fxx. fxx is just 2. Our fyy is 2. Our fxy is a derivative of fx with respect to y, which is 1, and our fyx, this is a coincidence that they're both equal to 2. Our fyx is taking the derivative of fy with respect to x, and that's just 1. So this being equal is not a coincidence. This being equal is a coincidence. So I'll put coincidence here. It's not usually equal to each other like that. In any case, what we're looking at is our D function, our discriminant or determinant or whatever you want to call it, is fxx, that's a 2, fyy is a 2, minus fxy quantity squared. And normally when we do these problems, we sometimes would have x and y variables here, but in this case we don't. So this is just a constant. I can't even figure this out. Let's just say this is positive. So what is it? 7, 4, 3? So it's positive. And according to this, if we have a positive value, then we have to double check our fxx. So this is positive, so we need fxx, which is equal to 2, which again is positive. And so we got a positive and they're underlining things again that look like that. Positive and a positive, so we have a local minimum. Local min at 1/3, comma, negative 2/3. Okay? Well, it turns out that this is just a paraboloid of some sort. And so paraboloid is just goes in one direction, so it only has one maximum or minimum. But we can certainly double check using I thought I had this ready already. Using our 3D plotter. You guys work on this over break? Just mess around? I'm glad some of you are honest. All right, we have x squared, xy, y squared, and y. So x squared plus x times y plus y squared. These are all pluses. So there's no surprise, it's just a parabola. But what's interesting really is to look at the contour plots as well. It's, you can also trace it. What was our critical point? Positive 1/3 and negative 2/3. I don't know how close I can get there. That's just too hard. And so let's do a contour plot. Did anybody figure out the y value, the z value for that, by the way? No, huh? Let's just go with this and see what happens. So somewhere over there, right in the middle of those concentric ellipses would be our maximum or minimum in this case. It's, look, 0.33 and negative 0.67. So that's your critical point from your function. All right, good. So that gives us another method of finding the max or mins using level curves. It's kind of interesting to see how these max and mins occur. And it turns out that if you have these enclosed circles or ellipses or things like that, these shapes, you can try to identify the maximum or minimum. I don't know where to put this. You can try to identify the maximum or minimum by looking at the center of those concentric circles or ellipses, it turns out. So saddle points are interesting also because you can try to, their level curves look different. And we have our famous saddle point, the x squared minus y squared saddle point, right? Do you remember how level curves look like? Hyperbolas, they're hyperbolas, but then right at the middle, there's a big X, right? So that big X is where the saddle point is. And so that turns out that when you draw level curves and you see an X somewhere in your level curves, there's a good chance that that's going to be a saddle point. All right, let's do another one since we got the work done for number 9 already to find our critical points, and we have 4 of them, so that should be exciting. We have 4 critical points to check. Let's check what kind of critical points they are. The question is usually said, find and classify the critical points. When you classify the critical points, you're actually finding out whether they're max or mins or saddles, or maybe you just don't know what they are. So let's do another example. So we need to go through and find our derivatives again and find our second order partials to construct our determinant, our d function. So our fx is 6xy minus 12x, and our fy equals 3y squared plus 3x squared minus 12y. Is that right? So our fxx, this is more of a representative example. Take the derivative of fx with respect to x. So x is the variable. I have 6y minus 12. Our fyy, take the derivative of this. This shouldn't be the same. Not necessarily. It might be the same, huh? Oh, I got to find something that's not coincidentally the same. 6y minus 12. Coincidence. fxy, the derivative of this with respect to y is just 6, and now not a coincidence. Oh, fx. fx with respect to y is 6x. And the derivative of fy with respect to x is also going to be 6x. I'm not going to put that down. It might look too confusing. So these are the 3 things that we need to find our discriminant or our determinant. And our d is going to equal to 6y minus 12, 6y minus 12, minus 6x quantity squared. All right, well, we got 4 points to do. So let's run through them. 0, 0. So d of 0, 0 equals negative 12, negative 12, minus 0, so positive 144. Let's just say it's positive. Okay, so remember that if it's positive, you want to put it back into the fxx, to see if the signs remain the same or if they change. So your fxx evaluated at 0, 0 in for x, there's no x. There's 0 in for y, you get negative 12. Whether it doesn't matter, the point that it's negative, it's less than 0. So your signs change. So your second derivative essentially is a negative. Negative concave down, so we have a local max. Okay. All right, 0, 4. So 0 again for the x, we're looking at this, and 4 for the y. So 24, 24, and 0. So 24 squared, positive. So again, we need to check our fxx. And fxx is this, so we put 4 in for the y, we get 24 minus 12, positive. So now the signs remain the same, so we have a positive second derivative. Positive second derivative, it's concave up, so we have a local min. Okay. All right, let's try 2, 2. So 2 in, we got 12 minus 12, 12 minus 12, that's 0 minus, and then this is going to be 144 or whatever. But the fact is that this has a negative in front of it, and so this is a saddle point. And I think if you do the same sort of work, you get another saddle. At negative 2, 2. So there, classified. So we found the critical points, we classified them, and we're done. Only other thing to do is to check to see how it would look like in an actual graph. Okay?
So, do we have the information necessary to say if those maximum minutes are absolute?
No, because we don't know what's happening for the rest of the graph. You know, for all we know, this could be like an exponential or a cubic function where it goes up and down both ways. And if in that case, then these are neither absolutes. If we restrict it to a closed region, then we can find an absolute maximum by just checking the values. Yeah.
So when you go up in more dimensions, I'm assuming your matrix is going to change and you just have to adjust your one matrix.
Yeah.
But when you go down and you go do the same idea to find this in 2 dimensions, how would you do that then? Like using this to find not our normal way, our Calc 1 way, but how would you use this for 2 dimensions?
Well, technically, it's still Calc 1. If you look at Calculus 1, applications of differentiation, finding maximum, minimum values, maybe shape of the graph, increasing, decreasing, first derivative test. So in Calc 1, the second derivative test looks like this. So f prime of c is equal to 0 says that it's a critical point. And then if the second derivative is bigger than 0, it's concave up, so it's a local min. If the second derivative is less than 0, it's concave down, so it's a local max.
Right, but how would you write the matrices that's associated with that?
It will be a 1-by-1 matrix, and that would just be the second derivative.
So there's no actual D for this
Well, the d would be the second derivative.
by itself?
Yes.
Okay.
Except we wouldn't call it d because it's called the second derivative.
Right.
All right. Questions? Oh, we're going to take a look at the picture. The function, it's a long function, y cubed. I'm not going to remember that. Oh, man. So our function is y cubed plus 3x squared y. I should know that. That's times. Minus 6x squared minus 6y squared plus 2. And we have critical points that are maybe we need to extend our critical points a little bit. Let's zoom out. All right, maybe we need to adjust. So you should just zoom out more. Just keep, oh, zoom out. That's not very helpful. I'm interested in shrinking the z, or making the z go up higher and lower. So maybe you go to negative 20 to positive 20. And I think if we scale it down, 0.5, 0.2, 5. There it goes. That looks okay. Still hard to see, but if you clear some of this stuff out, like maybe get rid of the box around the plot, you might be able to see it a little bit better. Remember how to make it transparent? I forgot. Here? Oh, yeah, here. Make surface transparent. I don't know if that helps. What would help is that if we just found a contour plot. Wait, before we find the contour plot, what are some of our critical points? 0, 0. This gives me the z value up on top here. 0 what? 0, 4. It gives me a z value of negative 29. 2, 2. Negative 14. So it just goes down negative. Oh, yeah, there's a dot over here. All right. So I just want to make sure in my level curves I want to include negative 29 or negative 30. So let's draw some contours that are kind of rough. Negative 30. Negative 29, negative 28, and let's jump to, I forgot what the other ones were, negative 14 or something, negative 15, negative 14, negative 13, maybe squeeze in a negative 16 here. And then I think it's the ones over here are close to 0, right? So negative 2, negative 1, 0, 1, 2, 3, 4. Maybe that's good enough. So I don't know what the best view here is. So let's see. Maybe we'll take a look at this view like this. And the scatter plot, you can kind of see the scatter plot. Kind of looks interesting. But let's point out some of those critical points from the scatter plot. So we got the max and min at these points, right? And then now I want to highlight this x over here. It looks more like a plus, right? Turn your head diagonal, looks like an x. In any case, those are going to be your saddles, right? So we got saddles over here. And then we got, I don't know which one was the max and which one was the min. Oops. And then if we match that up with the graph, oh, I cut the other one off. Maybe that's the best we can do. No, we can do better, but that's all I'm going to do. We can make these connections where we would find our minimum and our maximum. And then over here would be one of the saddle points, and then the other one would be just on the other side of that. That looks like a big mess. I'd like to say you get the picture. But let's get the saddle point from a closer view here. So the saddle point would be right here where it goes down. It looks like it goes down, but if we look at it from another angle, it looks like it's up. So right over here is where the saddle point is. In fact, we can put the dot there. See the dot? Put it right by the saddle, and it's sitting right here. Okay? All right. So that's how you would find and classify your critical points. And so now let's talk about absolute. Daniel asked a question about whether you're going to know this is an absolute max or min. In this case, we couldn't really tell, but now that we have the graph up here, it looks like the graph continues on forever up and forever down. And so it's neither a max or a min if we consider the whole domain. But if we cut this off at some finite region, closed region, then we could possibly find a max and min. So let's do that. Not this function. Let's find another problem. Back to our textbook. So these problems over here are questions where you're asked to find the absolute max and min because you're given a closed domain. So we can pick a problem between 29 and 36. 34. I'll do 34. So the theory here is explained in Calc 1 through what we call the extreme value theorem, where they say if you have a closed interval, you're guaranteed a maximum and a minimum. So the maximum could possibly happen at a critical point, or it could happen at the end point. And back in Calc 1, that was easy to figure out the critical points and the end points. Over here, the end points are a little bit trickier because your end points are not just 2 points at either end, right? It describes a region in 2 dimensions. And so what we need to do is we need to take a closer look at your domain. And here, x is positive, y is positive, so we know we're in the first quadrant. And then x squared plus y squared is less than or equal to 3. So you have a circle of radius 3, and you're looking at all the points in here. And we also want to include the boundaries. So your absolute maximum and minimum can happen inside of this, or it can happen right on the boundary of this. And that's what we have to check for. So let's first find the critical points. So we need our fx and fy. Fx is y squared. Fy is 2xy. And so when fx is equal to 0, then you put that in here, 2x, 0. Looks like x can be anything, right? So y is equal to 0, but that's just the boundary. Oops, that's this boundary. Y is equal to 0. We'll have to check that anyways. And then, so there's no significant critical points within this region that we're looking at. So there's really not much more to check. So now we need to check the regions or the boundaries. So let's check on the easy boundaries first. So let's check on this boundary here. So let's label this boundary 1. The boundary 1 is y is equal to 0 for x values that are between 0 and square root of 3. So what we'll have here is if you put 0 in for x, or sorry, 0 in for y, what you have here would be, well, I thought it was going to be a function of x, but it turns out that being multiplied together, that just becomes 0. So it looks like around here I'll just have a z value of 0, and there's not much to do there. All right, let's take a look at boundary number 2. And this time x is equal to 0 for y values that are between 0 and square root of 3. And so that, oh man, it's again going to be 0. So it looks like I have a z value of 0 here along this line as well. So let's see if this is at all going to get interesting. The last boundary to look at would be the third boundary here, which is the part of the circle that we're dealing with. So what we want to do is we want to look at this third boundary where x squared plus y squared is equal to not less than or equal to, but actually equal to, that gives us the boundary itself. That's the part of the circle. And we can just say x and y are positive, so we don't have to deal with other stuff. So we can solve for one of them. It looks like there's a y squared here, so maybe if I solve for y squared, I don't have to take the square root of this. So I have f of x and y. And now if I replace this, it's just going to become a function of one variable. Maybe I'll write this as a function of just x, where x is just x and y squared is 3 minus x squared. So now I just have a function of x. And now I can say my x value goes from 0 to square root of 3. So now I want to find the absolute maximum and minimum within this region over here. So how would I do that? I would probably take G, find a derivative so I can find critical points. And then once I find the critical points, what's the critical points? Plus or minus 1. So if I factor out a 3, I get 1 minus x squared, and then that's going to be x is equal to plus or minus 1. So if I look back at my domain here, is 1 within this domain? Yeah, because square root of 3 is bigger than 1, so 1 is in there. Is negative 1 in this domain? No, so negative 1 is not in the domain. So then I'm interested in finding out what happens at the critical point. So critical point that's meaningful for us is x is equal to 1. And so when I put x is equal to 1 back into the g function, I get 2. Now, I'm also interested in finding out what happens at the endpoints. So what happens at the endpoints? G of 0 equals 0. G of square root of 3 square root of 3, that's 0 also, right? So that's 0. So it looks like my minimum is just 0. It's 0 all over the place, and then I have an absolute max here. So my absolute max, I guess I should be clear, my absolute maximum is 2, but where is the point? I got x is equal to 1, right? What's y equal to? Y equals what? Square root of 2, right? And we can just ignore the negative because, because we just want positive values. And then our z value looks like it's going to be 2, right? So that's how we got this value. But if you want to put 1 comma square root of 2 into the original equation, you'll also get 2. And then our minimum looks like it's just going to be 0. So you got a bunch of places where it's equal to 0. Looks like it's going to be equal to 0 along 2 of those boundaries. All right? Yeah?
So if you get critical numbers for a bunch of these other things, it can get really complicated. And like,
Oh, yeah.
okay.
Oh, no. If you get critical numbers for the boundaries, then all you have to do is check what the height is.
Right, but
So-
if there's like don't you have to check the height for all of those boundaries?
Yeah.
To see which one's the highest?
Yeah.
Okay.
Yeah. So you guys want to see a graph of this, or let's quickly see a graph of this. This is just xy squared, right? That's an easy function. Oh, we want to cut it at the domain, so I don't think I can cut a circle out of this, but if I just say I'm going to go from 0 to, what's square root of 3? Square root of 3? 1.57? 1 point, what is it? 7.3. 0, 1.73. And I probably didn't need to go all the way up to so this is how it would look like, but what we have to imagine is we have to imagine that it's being cut by a cylinder. And so
Oh, like it just goes inside and hits all the boundaries kind of stuff?
yeah, so let's see, parametric surface, x, cosine u, sine u, b, u goes from 0 to pi over 2, and v goes from 0 to 2. Oh, what's square root of 3 again? 1.7? So here goes. If you imagine, come on. So if you imagine this curve over here, can't really see it now because they're both kind of light. So that circle forms this cylinder, and if you imagine the intersection between that cylinder and the surface, the maximum point is going to be at this highest point when x is equal to 1 and y is equal to 2, apparently. And so that's how you would get that maximum value. And then the minimum value is just 0 all around here on the boundaries for the x-axis and the y-axis, and 0, 0. Okay? All right. I will post the video of that presentation that I did, and I will consider this section done then, although we didn't finish it in this lecture. You can see another example of classifying critical points, finding the absolute max and mins, and then one application problem to geometry that is in your homework. So hopefully that'll help. And then tomorrow we'll talk about the next section. What are you talking about?
The last two questions.
Oh yeah, I have to look for it.
You don't have it?
I was wondering, I didn't get a point for the Haley's comment thing. Do I not get a point for that?